Can everyone see that?
We sure can.
Cool. Okay, so hi, my name is Alvarado Rodriguez. I'm a software engineer here at Hewlett Packard Enterprise working with the advanced programming team. And I'll be presenting our work today on towards a general aggregation framework in Chapel. So in distributed memory parallel programming, one of the most common bottlenecks that exists is the quantity of communications performed between remote parallel tasks. Increases in communication can be especially seen in irregular workloads, such as those that use sparse matrices and graphs. For this talk, the focus will be on optimizing sparse matrix creation via a prototype for general aggregation, but we'll also be taking a minor look at sparse matrix multiplication and RMAT matrix generators for background. Chapel has a copy aggregation module to facilitate the batching of fine-grained communications for array-specific operations. However, there is not a more general framework to support the aggregation of more user-specific operations on data structures such as lists, etc. We will introduce a framework prototype for more general aggregation. The work for this talk did not only involve the framework prototype. I had to go in and add parallel safety into the compressed parse. Layouts are available in Chapel for two-dimensional representations of arrays. And I also had to go in and look at the sparse domain buffer functionality to add in flags for uniqueness and sortedness to increase the performance of adding in the indices into sparse domains. The motivating use case behind this work is sparse operations in Arkouda. I just realized that I don't have any slides introducing Arkouda. Arkouda is basically a library in Python for NumPy and pandas-like operations at scale on distributed arrays. And its backend is written in Chapel and its front end is through Python. Through a code like this one right here, if my slides advance, say that you create PD arrays in Arkouda, which just stands for parallel and distributed arrays. Say you have rows, calls, and vals, where rows and calls are just the indices of the two-dimensional sparse domain that you want to create, and vals are just some random values. Once you have those, you can create a sparse and matrix with those indices by calling this function here. In this sense, we create A in the layout of CSR, and then we create B with the layout of CSE. If you haven't heard of CompressedSparseRow or CompressedSparseColumn before, I'll have some slides that talk about that in just a bit. Then you take A and B, you times them together, and then you end up with a new two-dimensional array C. In Arkouda currently, the CSR creation and the CSE creation steps will take more than the multiplication steps themselves. As you can see here in the gray box, we have about 50 seconds, and both of the creations take a little over 60. With our work with creating this general framework for aggregation, we've been able to reduce the execution time with about 34x for this example here on an HP Cray EX system on 64 locales with on 64 locales. So some background. First, you may be asking yourself, what is aggregation? Aggregation is basically just taking something that lives remotely, putting it into a buffer, and then flushing that buffer and dragging that that value over to where you want it to be stored. In this example, I took this straight from the documentation we have for aggregators in Chapel. We have an array A, assign the main values of 1 to 1,000, and then reversed array RA, where we basically just want to reverse the array A. You would do that with this for loop right here, where we instantiate an aggregator with that with statement there. And then for every iteration of this, we will move the value from A size -1, which is our source destination, which is our source of where that element lives, and then we're going to move it to RA. So if you aren't aware of how for loops work in Chapel, they will spawn a source aggregator per task. Therefore, these are per task buffers for every locale for every task, which makes aggregation a little bit RAM intensive, but you end up getting a lot of performance. In this case, as I said, the destination is RA, and we're using a source aggregator because our source, which is A size minus I, is what is remote. And here I show source aggregation, but the rest of the talk focuses on destination aggregation. And then, as I said, whenever the buffer gets full or all the iterations of the task are finished, then a flush gets issued. That's a typo. That moves all the saved values in the buffer to the memory location that they belong in. We used a special type of graph for this, for the experimentation, called a power law graph, where basically you give the generator a number of vertices or matrix elements. I'm a graph person, so I see a matrix and I immediately think graph, where we want the vertices or the cells that are filled to be 2 to the scale. And then the edges are 2 to the scale times some constant edge factor. The way that this works is that you split the adjacency matrix into 4 equal parts. You choose a part, you subdivide again into 4 equal parts. And then once you reach a 1 by 1 cell, you assign it a 0 or a 1 based on some probability if you want to keep that edge or not. The probabilities, when you set them to the values here, A 0.57, B, C 0.19, and D 0.05 gives you a Kronecker graph, which is specified in the graph 500 specification, that gives you a graph that exhibits a power law vertex degree distribution. And that basically just means that a vertex or a subset of vertices, a subset of cells, are connected to all the other cells. And then this makes it an ideal random graph for benchmarking. So I've been talking about layouts, compressed sparse row, compressed sparse column, etc. Now we'll just present them in more details. One of the more common ones is the coordinate format, COO, where you basically just explicitly store all the row indices and all the column indices, and then the values array just stores the value stored at that location right there. So here we see we have row index 1, column index 2, 1, 2, and we have values stored 1 there. One of the more common ones for HPC is compressed sparse row format, where instead of explicitly storing all the row indices, you just store the row starts, and then you store all the column indices. This basically just means that row 1 starts at index 1 instead of values and column indices, and that ends at index 2. So yeah, so then that gives us that that row 1 at index 1 has value 1, and the column index is 2, so that's the one right there. And then the other one is also an equal 1, but if we look at between 3 and 6, that means that row 3 starts at index 3 and ends at index 6, which means that it has 3 values associated with those columns, which would be 3, 4, and 5, as you see right here. And then so on and so forth. And then compressed parse column, CSE format. It's basically the same exact thing. Instead of storing the row starts, you store the column starts. And then it's the same thing basically, where column 1 starts at index 1 and it ends at index 3. That means that we store 3 rows within that column with values 6 and 8, which you can see here, column 1, value 6 and 8. And then say you want to multiply 2 of these together. we have this little GIF figure right here, where we have a matrix in our left-hand side with CSV storage, and then another one on our right-hand side with CSR storage. The same general rules apply when you're multiplying two of these together. We do column 1 by row 1. Transposing these over here so it's easier to see the multiplication take place. We find the intersection, and then we just multiply 6 by 1, we get 6, and then 8 by 1, and we get 8. And then that gives us the first filling of our resulting graph C, matrix C. Then we do the same thing for column 2 with row 2. Transposing them over here again for easier view. 1 times 2 is 2, 7 times 2 is 14, and then so on and so forth until the entire until all the resulting cells are filled. So our proposed solution for general aggregation is that instead of trying to make something new, we can just take the current copy aggregation module that exists in Chapel, and we can change it a bit to accept 2 new user-defined records. These 2 user-defined records are the source handler and the destination handler. The source handler dictates where the data is going to be transferred to and how it will be stored within the buffer, and that the destination handler will perform a flushing operation to physically move the data from the buffers to their physical memory location on the compute node that they should be on. This gives more power to the users to let them specify what data structures they want to aggregate into and how the data should be treated. So first, let's look at the source handler. It's a record where you need to specify 2 main functions, source copy and get destination locale. In line 4, we have the expected format for the source data. And eventually, this is also how the destination locale will know to add index ij to the sparse domain and then value v to store within ij. Then in line 6 through 12, the initializer extracts the underlying record for domains and arrays. This is a workaround that's currently classes in Chapel do not let us take a ref or a pointer of a domain or array. Then lines 14 through 16, the aggregator has a backend handler that uses this function to instantiate a destination handler whenever it comes time to perform a flush. So when it comes time to perform a flush, the source handler issues a source copy, which returns a destination handler on the compute node that will move the buffers over and then perform the flush operation there. And then lines 18 through 21 gets the locale that owns the index ij. So that way we
Oliver, you got muted.
Thank you for catching that, Lydia.
Can everyone hear me now?
Yes.
My headset died. That's cool.
Ah.
Sorry about that. I charged it too. Well, that's sad. Okay. Let me reshare now. Okay, there we go. Sorry about that. So the source handler, I think you guys heard me say lines 14 through 16. Yeah, so then lines 18 through 21 gets the locale that owns index ij during a copy step. And then that is used to add the full tuple igv to the buffer. So now I'll talk about the destination handler itself. As you can see, it's pretty detailed, but I'll break it down line by line, basically. And then in lines 53 through 54, you can see how you can instantiate the custom destination aggregator with a source handler, and then you call it to copy over I, J, and V. In lines 32 through 45, we have the works for the flushing operation itself. It's currently a lot more scary looking than intended. I just couldn't help myself and I wanted to optimize it as much as possible. Lines 33 through 34, we create an index buffer for faster addition of indices into a sparse domain. Lines 35 through 39, we add a given index ij into the buffer. Once the buffer is full or hits the commit in line 40, the buffer gets flushed and those indices get added into the domain. I do want to point out that this is not the same as a remote buffer within the aggregator. It's its own buffer to make additions into sparse domains faster. Then we have in lines 41 through 45, once the indices have been added, we add in the actual data itself, which requires finding the index for ij in the backend array that stores that data. And then lastly, in lines 53 through 54, we see the aggregation prototype in action. So now I'm going to show some results. First, I will show the aggregated versus non-aggregated sparse matrix creation time results. These results were taken on an HPE Cray EX supercomputer. And then we use RMAT scales 14 through 18 for the random graphs we use for this experimentation. We see consistent speedups across all scales for the aggregated construction times versus the current Arkouda construction times. The speedup for CSR is greater because CNC non-aggregated construction was generally slower. I don't have a strong reason or sense of why, and I didn't want to speculate, but it would be a good study to figure out why. Generally, as the number of locales increased, the performance got better for aggregated construction, whereas the non-aggregated construction slightly degraded in performance as locales increased. There were some system-specific issues I ran into with the compute nodes that caused some odd results, like in the CAC construction at 121 locales, down here on the right, where the aggregated code did not perform as well as it should have, quote unquote. Rerunning the test with one trial showed that I got better performance, but I kept a bad result just to show that when you run into a system-specific issue, even if it doesn't affect the correctness, can affect the performance of the aggregated code. Now I compare the multiplication itself against the creation on scales 14 through 18, just to show that the creation is always faster, which is what we want to see. So that way an Arkouda user does not have to spend a lot of time waiting for the data to be brought in. Rather, they can wait a long time for the operation that they're trying to carry out. Well, not a long time, a pretty decent time. Overall, the aggregated creation is always significantly faster. This is good for Arkouda users to quickly load in the data and immediately start their analysis without having to spend too much time waiting for the data to load. I present the y-axis on a log sub 2 scale. No specific reason, just that if you saw this not as a log scale, these bars would look like they were almost not there, even though it was consistently about 4x or faster. Now here I show what the largest scale was for each locale, for each count of locale. Here we see that the maximum scale for the RMAT graphs constructed. As a reminder, the matrices occupy an area of 2 to the scale by 2 to the scale, and the non-zero values are about 2 to the scale by 32. Give or take just a few repeated edges that get parsed out. If the scale is 20, then that will give a ratio of about 1 to 32,768, or a very small number of non-zero values. We can see that for the locales 25 through 36, the creation time significantly improved for scale 24. And then the same can be said for locales 49 through 81 for scale 25. And then 100 through 144 for scale 26. And then this just exhibits strong scalability for the aggregated sparse matrix creation code. A little fun fact is that graph scale 26 is considered a toy size by the Graph 500, but that's just because they run on supercomputers like Fugaku and Frontier. Assuming 64 bits per edge, a graph of this scale probably takes up about 20 gigs in RAM. So, in conclusion, I think I'm close to my time. I'll just show my conclusions. This is, oops. This is work that introduces early steps towards the general aggregation framework in Chapel. And going forward, looking into the future, it would be cool to have a comparison against state-of-the-art algorithms, tools like conveyors, a more in-depth look at the framework prototype itself. How well does it support source aggregation? What other workloads can it be applied to? And hyperparameter tuning. Aggregation has a ton of toggles like buffer sizes. Is there a special perfect place for buffer sizes to number of aggregations that is most optimal? But that's all I have.